Thanks so much, Greg, for the introduction. And I'm very excited to be here and thank the FluidTech team and sponsors to make this possible. And yeah, I'm excited to bring you through this presentation. So from the title, you can see we proposed a reliability as a service solution to our customers. And today I'm focusing on bearing failures. So it's not journal bearings, I'm focusing on the roller bearings. And here we look at the deciphering the lubricant and how the lubricant affects the failure. So our tool that we use is, or what we developed, I present the technology behind it, go really into detail, and then also give an explanation, example on it and where it's currently been used. So again, this is me. I mean, I look a little younger here, but that's okay. Photolines Fusion is located in London, Ontario. I'm located in Germany to do all the business out of here. And I don't have to be up at 6 o'clock or as late as Greg is up to moderate everything here. I can do it from like noon here in Germany. So anyways, let's get into the details here. So overall, the human consumption in the world has gone extremely up. And now in 2019, the resources that have been used are extremely high and have been 1.7 times what the nature can produce. So to make this sustainable in the future, the amount of to make this in the future, we really have to look what we are wasting or using, and this is where also tribology plays a large role. So here, with tribology, we can reduce a huge amount of consumption that is currently going on, especially like oil wastage, moving from calendar-based to evidence-based maintenance, and really making systems more efficient. Again, today I'm talking about bearing failures, and our technology focuses on the effect of the lubricant in the tribal system, so the surfaces that interact with each other in presence of electrical charges. So the electrical charges at an interface can occur due to systemic or localized events. The lubricant can charge by itself based on the articulation, or the electrical charges can be occurring in the system due to filter charging up, and that can affect the long-term performance of those bearings. So one of the factors that or failures have been associated with bearings is a very significant one and widely investigated over the last 30 years, called wide edging cracks. And on the right, you can see here that under the surface of a rolling element here, you can actually see how on the microscope it looks like you have these white lines under the surface, and that eventually causes the detachment of the particles. And the problem with wide edging crack is that it's suddenly occurring, and already down to 5 to 10%, 20% of the estimated lifetime. So it really strongly deviates from the Dean estimation of 281 that's used for estimating bearing life and applications. And when we look at gearboxes, it has a massive impact, especially on wind and marine drives that are highly cost intense, and you can't really plan the maintenance, because this damage can occur like irregularly. So the problem is here that wide edging crack has multiple factors, mechanisms, but it's now been agreed on the last 5 years, or more common knowledge is now the lubricant has a major effect on it. So whatever happens in the first even 1,000, 2,000 hours or a short period of time can cause a distortion on the surface. And that's in the presence of the lubricant and the electricity causing distortion on the surface, and then eventually wide edging cracks to develop due to further loading or water hydrogen ingress. But really today, I'm going to explain the background on the bearing failure on wide edging cracks, because this is a electrical charged failure mechanism. And here, wide edging cracks, just to show you briefly under the microscope, in rolling contact fatigue, you have different high angle bands, high and low angle bands that show, but in the wide edging crack area, it's a completely different damage mechanism. So really, just to show you like a different microscope, how these different failure mechanisms look like. Now, our technology focuses on, in the performance degradation curve, on the operational monitoring. So basically when the time the machine or the bearing is running until the first damage is detectable via first signs of oil analysis or vibration or any particle detection, right? So here we look at the damage onset, but also goes to time 0 and before. So we look at quality control as well. So we assess the lubricant composition based on the XFA, take this data, run it through our algorithms, and then come up with the risk assessment saying, okay, you have this type of lubricant with certain components in it or certain contaminants in it, you will experience this type of risk when you move forward. So no damage has occurred yet, but we have this algorithm that allows us to proactively assess it. So how does this work? So I'm taking you on a deep dive now, and I'm going into tribology. And tribology is really the science of cascading events. So when you have a wearing part and something happens after 1,000 hours, and after 2,000 hours it fails, it really, the event after 1,000 hours was had a huge impact on the life of this moving part. So it's important to have algorithms for cascading events that allows us to, in consideration of the science, to decipher the tribal system and apply the chemistry and bring it all together in predicting failure. So how do we do that? Well, we have proprietary mathematical modeling. These are the principles that are involved, looking at thermodynamics, reaction diffusion model, and these are all used and combined. We did this for over 15, 20 years into an equation, so to say, that allows us to simulate stress points over a certain application that occur. And then these stress points are the risk situations. So how does it work? So when we have a system where there's no relations, just to show for visibility here, how do these stress points develop? So we have just do random points on the left and let these develop for 10 seconds without any algorithm. So this there's no change in relations. However, on the right-hand side, we start up with the same type of randomness, but we apply it to our algorithms. And after a while, we'll see after 5 minutes that with the equations show us no relationship with the random data points, but with the CWorks algorithm, it shows us a stress point. So really, the system is converging towards one parameter. So this is very theoretical now, but to visualize this, especially in tribology, you have different situations, different stress points throughout the lifetime of a bearing or an articulation. So it's at one time, the stress point can be at very early on in a blue area. Then it can change again to a red area. Then you have a red-yellow area. And all these different colors eventually show you, okay, there's a stress point. This could be a risk. And how does that help us? Well, why are we doing this? We want to be proactive. So in healthcare, for example, everybody heard about precision medicine. You take the blood sample, you assess the blood, and then you come up with prescriptions. Okay, this patient is at this risk for this disease. Now we can schedule proactive treatment. So we take the similar approach in machine elements, where we look at precision reliability. So we determine the chemical composition of the lubricant, decipher it, run it through our algorithms, where we take account of the surfaces and the lubricant, and then predict, you will run into a risk under these certain conditions if you have electrical charge with these type of chemical compounds. So important is to see we're really proactive, same as in precision medicine. We take that analogy over into precision reliability, and that's what we provide in our cloud tool. Here you can see a little bit of a deeper dive how we have that set up. We receive parameters that are captured from the operation. that are then going to in our database where we look at the reasonable comparison. So we basically reverse engineer the oil through our algorithms. Then we check the plausibility. Is this the right composition? Yeah, it's very close. We reiterated it several times. And then we go in our knowledge center here. And in the knowledge center is where the first magic, so to say, happens. So all the science does the work. So we look at molecular modeling, we look at the data exploration, and look at the characteristics that have been recorded as well for these compounds. After that, we transfer the data into the steelworks and come up with, then run it through the algorithms, and then here come up with recommendations. So this is the core IP, where it runs the data, the chemical data, the analytics through the system to define or identify the risk that certain situations are at. So, and in the end, we give a proactive assessment. And going even deeper into it, we're looking at the of the modeling that's been performed. Is we're looking at the transcale modeling. It's very, very difficult to perform because you need extreme computational power. However, we designed an approach that allows us to reduce the complexity and allows us to speed up the effects or the characteristics of the transcale modeling, where allows us to go from the atom up to the application, right? So there's many assumptions been made, but it works well. And further reading can be done when you look at this paper down here that we published specifically on the reliability as a service in this year in the IoT journal. So basically we get the data, we run it through to the algorithms, and then we receive an output. And that output gives us a risk assessment. This is what you have to keep in mind, what the end user will get. So data in, we process it online, and you get a feedback back. And we've developed this in real world applications, as well as in laboratory test setup, where we did many tests, ran it in marine applications, automotive, did a lot of surface analysis, transitory microscopy, so very depth in analysis to validate this approach. And the infrastructure like this looks that we have a gearbox somewhere on a ship possibly. There's a sensor that gives us a trigger. Okay, at that time, the trigger tells us take an oil sample. We receive the oil analysis. We run the data through our prescriptive engine and give the end user recommendation what to use, what to do. So I've gone really fast now, I think, through all of this science, but now I would like to show you on a practical example how this works. So here we have a drivetrain on a wind turbine, and the samples, oil samples were drawn at different locations. So we have the fresh oil and the oil at different locations. And we conducted refractive index analyses as well as other analyses, and then performed our assessment of the reliability. So these samples were then drawn after our sensor, our trigger, which is the refractive index sensor, triggered, okay, something has changed in this situation. You should take an oil sample now. And the nice thing about refractive index is that it's a very high resolution, very accurate, very sensitive technology that's established by our partners, Schmidt and Hensch, and we'll use those in the future to put that into line and assess the changes of an application. And then we have the oil samples run through our system. So that's our partner we'll work with. And when we looked at the refractive index of the fresh oil in this application, there was about 14701. And then the contaminated oil showed a trigger that went where it significantly changed. And this change then suggested to, okay, now you have to draw a sample, do the offline analysis, and do the data processing. And in my point of view, we will always be at this status of having online and offline combined, because the depth of information you get from the camera analysis, in my point of view, is just so much deeper than having the purely online sensors for triggers and detection. I think the combination of both is the best solution. Then we looked at the infrared spectra, and we saw only a few changes, but also there was some sort of indication that there was water ingress. When we looked then at the X-ray fluorescence of these samples, fresh and new ones, we could see there was a lot of chloride coming into the measurement, and this is probably due to the saltwater ingress. And this was already a great information to see. However, we wanted to look deeper and see really what has changed. And the next depth was to look at chromatography, and this really allowed us to see, okay, there is contaminants. Where's the bandwidth of the contaminants? And this allowed us to also identify that there's detergents and kerosene ingress into this drivetrain. Now, when we run the information that we received from the analysis, we only need the online trigger, which is the refractive index, and the XFA analysis to give you information on the risk, the risk of the lubricant under electrical charge. When we look at the compounds, so the base oil additives by itself, then there was no risk for wide edging cracks. However, when we did combinations of these, combined these base oils and the additives, we could see that even the fresh oil was at risk, and water ingress even further put the application even at higher risk. So using COX right in the beginning was able to tell us that there was an inherent risk of the lubricant, and countermeasures should have been taken at that point right away. We have also been involved in a publicly funded project with multiple industrial partners, and this was a project that was just finished this year, and further publications are to come. There we assessed as well the fresh oil of the wind turbine together with the used oils, looked at the contamination and assessed the risk for failure that are mediated through electrical charges. So, and here there's also further reading that I recommend. Our paper, of course, as first, and then the paper by the University of Aachen here with the group with Dr. Jacobs, and also our white paper that we published earlier this year in the Bearing News publication. So these are, this is just a condensed information here. Important, the main message is that we look at the lubricant, the risk of the lubricant before damage occurs, and this has been validated and applied. So this allows you to take measures right when the lubricant, for example, is shipped to a different location. Is there water ingress or other contaminants come in? How's the risk of my lubricant? And also at the early stages of operation, when the lubricant has been filled and replaced after washing of the application. How's the risk after early running? Has that changed? There's a lot of quality control, but also very proactive in saying, you know, if you have the certain condition with electrical charges that could occur, you run into this risk. And that's went through, it's like 20 minutes on the button.